Hello everyone. So in this session, I want to answer this question whether and when both phi, the velocity potential, and psi or stream function exist in a flow. So what are the conditions that in such conditions both of these exist in a flow and we can use both of them to find the streamlines and velocity potential in those flows. Okay, so if you remember from when we kind of define these two functions, velocity potential can be defined for any irrotational flow. Okay, so the only condition for a velocity potential is irrotationality of the flow. As long as it is irrotational, then it can be defined. So for stream functions, or stream function, it can be defined for any two-dimensional, so the flow had to be two-dimensional and incompressible flow. Okay, so these are the conditions for defining a stream function. So now where both phi and psi can exist, they can exist for any, if these two conditions are met at the same time. So for any two-dimensional irrotational and incompressible flow, both phi and psi exist. Okay. So this is the condition for if we have a flow which is 2D, irrotational and incompressible, both phi and psi exist for that. Okay, so let's see what does this entail. So first of all, I want to write irrotationality conditions. So we have irrotational flow. That means the vorticity or curl of velocity should be 0. The second one is incompressibility. So the divergence of velocity grad dot v has to be 0. And then the third condition is we have to have a two-dimensional flow. It shouldn't be like a three-dimensional flow. These only exist, the stream function only exists for a two-dimensional flow. Okay. So what do these mean? These mean and imply that, first of all, we will have an equation for phi, which is a linear Laplace's equation. So grad square Laplacian of phi equals to 0. And here we showed that if the flow is also irrotational for stream functions, we can also write these conditions. So grad square psi or Laplacian of psi is also going to be 0 for this system when we have irrotational flows as well. So this is interesting because now we have two linear systems, and we can say phi and psi are both harmonic. Right? Like they can be cosine, sine, these kind of things of functions, because these sine and cosine, they can cancel out. So these are harmonic. Phi and psi are harmonic based on this. So this is the equation that we have, and so now I want to show how these look like, and in terms of velocity. First, in the Cartesian coordinate, so in Cartesian coordinate, we can write u is partial phi over partial x, which equals to, in terms of psi, it's going to be partial psi over partial y, right? This is how we define phi and psi. And v, the velocity component in the y direction, is going to be partial phi over partial y which is going to be minus partial psi over partial x. We can look at that. The way we define that, so this is, yeah, v is minus partial psi over partial x, and u is partial psi over partial y. And for phi, we did a similar, our definition is, yeah, u is going to be partial phi partial x, and v is going to be partial phi partial y. Okay, so these are the definitions we had for Cartesian coordinate. Or we can define this in cylindrical coordinates. So let's see, or in cylindrical coordinate. In cylindrical coordinate, it's going to be as follows. So first we have radial velocity. So the radial velocity UR is going to be partial phi over partial r, which is going to be 1 over r partial psi over partial theta. These are how we define it in the cylindrical coordinates. And u theta, which is the tangential velocity, is going to be 1 over r partial phi over partial theta, which equals to minus partial psi over partial r. Okay, so this is how we have these two systems now, and this system is known as, these system of equations are known as Cauchy-Riemann equations. Okay, so these are very helpful because they are going to help us a lot to solve some canonical fluid problems. So let's get started with one simple example, and then we can move forward to a more general way of representing these. Okay, so the example I want to solve is example for a potential vortex. So the question is, find velocity potential and psi stream function for a flow with circular streamlines let me say for a potential vortex, this is easier, and then I'm going to explain what is this for a potential vortex. So a potential vortex is a flow with circular streamlines around a common axis where the velocity distribution is such that curl of velocity or the vorticity is going to be 0. Okay, so we can define these phi and psi for both of them, right? Because if the vorticity is not 0, the flow is not irrotational, and so we cannot define this. Okay, so let's look at this, how this looks like. So if we have, let me plot this. So now we can have different streamlines. So I'm going to plot 3 of that. Okay. So the way it works is as follows. So we have these kind of circular streamlines that are kind of rotating around the common axis here. Okay. So now we want to find phi and psi for this flow, for this potential vortex. So as you see, this flow is two-dimensional. Also, as it's given, the curl of velocity, which is going to be vorticity is 0, and because this is a two-dimensional flow, the only component of the vorticity that exists is in the z direction, right? So if this is x direction and this is y direction, the only component that exists for the vorticity is in the z direction, meaning that the flow is rotating around this axis. So let me put it here. We have x, y, and the only component of vorticity is in the z direction, which is going to be what? Which is going to be for, in terms of cylindrical coordinate, and let's do it for that because this is a circular motion. We have it here. Let me just copy this, the last component. Only the last component, so I'm going to remove this part. So this equals to this component, which we know based on the problem statement, it's going to be 0. And also a potential vortex has circular symmetry. So any variable, because it is symmetric in this theta direction, right? If you take, that means it's not going to change anything, nothing is going to change in this theta direction, right? It's going to stay constant because we have a symmetry, we have a homogeneous flow in the theta direction. So the gradient of any variable with respect to theta is going to be 0, right? Because it's not changing. It's not changing over this theta. We have the kind of a circular symmetry here. Okay, so the partial over partial theta of any variable, it doesn't matter. It could be velocity, all velocities. These all will be kind of their gradient in the theta direction is going to be 0 because of this circular symmetry. Okay. Or homogeneity in the theta direction. So let's see what does this mean. So it means here in the theta equations, so let me write this down again. So I can write, this means that this should be 0, right? And because we have a partial over partial theta here, so this term is going to be 0. And so this means that partial RU theta over partial R is going to be 0. And so this means that RU theta is constant. So by convention, we set this constant to this over 2 pi, where this symbol is called circulation. So circulation over 2 pi, which kind of shows the strength of the vortex. So this shows the strength of the vortex. So if the circulation is larger, the vortex is going to be stronger. So if this circulation is positive, for this, we define this to be positive for counterclockwise rotation. And here the U theta is going to be circulation over 2 pi r based on this. Okay, you just set that constant to that. And so now let's find these psi and phi for this flow. So we have U theta is just going to be circulation amount, which is a constant, over 2 pi r. So when r is 0, it's going to be smaller, it's going to be larger, the largest velocity, and as r goes to infinity, the U theta is going to be about 0. So U theta is the circulation over 2 pi r, and now I write it based on these equations that I had. So first I want to write it in terms of, I need to use this equation, so I will just put it here so you see what I'm doing. So first for phi is going to be 1 over r of partial phi over partial theta. So as you see, these r's are going to cancel out. And so phi is going to be circulation times theta over 2 pi. So let's see what is this. Circulation times theta over 2 pi. So it's just a function of theta. So if you want to show the first streamline, the first theta, the phi velocity potential is going to be like this. So this could be, say, phi 1, and then this is going to increase with theta, so the next one can be something like this. So let me also change the style. Okay, and then this is going to be phi 2, which has a different theta, right? So this is like the theta here. So the theta is increasing, so this phi is going to increase. And as you see, if this is the velocity, the velocity is going to go from lower potential to higher potential. So this phi is smaller, and then this phi 2 is going to be larger because we are in the correct, theta is going to increase. So the velocity is going to go this way, and so on and so forth. You can have other phi's, right? So this is how this looks like. Now let's go to the psi. So this was velocity potential. So let's look at psi. So for psi, we have u theta, which is circulation, over 2 pi r equals to minus partial psi over partial r. So this means that psi is going to be minus partial over 2 pi of ln of r if you take the integral of this. This is interesting. This means that the psi is only a function of radius. So phi was the function of theta, and psi is only a function of radius. So meaning that psi is going to be, as at each r, it's going to be constant, right? So I forgot to do this here. So let me see. This is going to be the direction of the velocity. So phi, the psi is going to be constant at each r. So these are actually going to be my psi's. So these circles I have shown, because they are at certain radius, these are going to be psi's, each of these circles, because they are as a function of r, okay? And as r increases, the magnitude of psi increases, but it's the sign is going to be more and more negative, right? Because it's r is going to increase logarithmically, okay? So this is going how the stream functions would look like. So the flow will be like moving around these circles in this potential vortex, because psi's or the stream functions actually show the streamline and how the flow moves around, okay? So this is going to be the psi and phi, and they are again perpendicular to each other, as we see. And this is how you can solve this together for a flow. And now, in the next lecture, I'm going to define complex potential, which is going to give us the harmonic solutions for these stream functions, and which is going to simplify our methodology for solving these kind of canonical fluid problems. Okay, so let me wrap up what we learned today. So we started with stream functions. So we defined for a two-dimensional incompressible flow, we can write the continuity equation, and based on the continuity equation, we define stream function, which is here because that's going to satisfy continuity equation. So it's not necessarily need to be a rotational for stream functions to exist, unlike the velocity potential. But unlike velocity potentials that are valid for 3D flow, stream functions are only exist for two-dimensional flows. And then we talked about the properties of psi. So the psi constant just shows the streamlines of the flow. And the difference between two psi or two stream functions show how much volume flow rate you have between those streamlines. And we showed that the lines with psi constant and phi constant are orthogonal, so they are perpendicular. And if the flow is also irrotational, in addition to 2D and incompressible, then we showed that the Laplacian of the psi is going to be 0, so this is going to also give us a linear equation. And then we talked about where both phi and psi exist. They exist, a velocity potential exists for any irrotational flow, stream function exists for any two-dimensional incompressible flow. So for any 2D rotational and incompressible flow, both of these quantities are going to exist. So we have this condition. Under these conditions, phi and psi are going to be harmonic. And so we showed this in Cartesian coordinate and cylindrical coordinate, that how these both of these look like. And these are known as Cauchy-Riemann equations. And then I showed an example for a potential vortex, that how do these look like and how do they actually exist together. So in a potential vortex, it's an irrotational flow, again, based on our definition where the vorticity is 0. So the flow will circle. It has circular streamlines around the common axis, but the velocity distribution is such that the curl of the velocity is 0. And we showed that for such a potential vortex, the tangential velocity should be a function of gamma or circulation over 2 pi r. And for these kind of flows, we found that the streamlines are going to just be these circles, and the velocity potentials are going to be perpendicular to these lines that indicate the velocity is potential, and the velocity goes from low potential to high potential. Okay, thank you very much. In the next lecture, I'm going to talk about complex potential and complex velocity phenomena. Thank you, everyone.